Hello everyone, my name is Yuan, and today I will present DICE, detailed inter-chiplet end-to-end fine modeling for accurate chiplet simulation. This is joint work with Rashid Aligholipour and Stefanos Kaxiras, and we are from Uppsala University, Sweden. This work has won all the 3 artifact badges in ISCA 2026. The main question behind this work is simple. When we simulate chiplet-based processors, are we modeling inter-chiplet communication with enough details to make architectural studies accurate? Let us begin with the motivation. Building a large monolithic processor has become increasingly difficult. We run into power and thermal limits, yield decreases as dice goes larger, and testing and verification becomes more expensive. Chiplet-based designs address these issues by splitting a processor into smaller chips. This can improve yield, make verification more modular, and allow different components to be reused or manufactured separately. But this introduces a new architectural problem. Communication now crosses chiplet boundaries. This crossing goes through technologies such as interposers, UCIe-alike interfaces, or proprietary fabrics such as Infinity Fabric. For architects, the important point is that these links are no longer just ordinary on-chip wires. They can add latency, variability, and reliability effects that influence performance. This talk will cover 5 parts. First, I will explain the scaling problem and why current simulators fall short in modeling chiplet-based architectures. Then I will introduce DICE. After that, I will walk through the design, show key results, and finish with the main conclusion. Let us first look at where the problem comes from. In a chiplet system, cores sit in a compute chip called the core complex die in AMD's terminology, where we have compute cores, caches, and a communication interface called the PHY link. A multicore system made of such chiplet consists of multiple copies of such CCDs. Further, memory or I/O functionalities sit in a separate die called the I/O die. Communication between these components goes through the PHY links in a serial manner. For example, when a core requests data from another core, the request first is sent to the local PHY link, then travels via the I/O die before landing on the destination, which can be another CCD. More importantly, inter-chiplet communication behaves more like a real physical channel. It has latency variations, it can experience noise, it may need error correction, and it can occasionally produce long latency tails. To model such a chiplet system, the common approach in architectural simulators for chiplet, such as heterogarnet, is to model these links with fixed latency. This is convenient, but it hides all the detailed behavior of PHY links. These behaviors matter because fixed average PHY latency is not enough, especially for evaluating LLC-intensive, synchronization-heavy workloads, where dependent load chains can amplify a few long-latency events into many stalled cycles. In the example shown here, we compare inter-chiplet packet latency for graph application BFS on a 4 CCDs, each CCD with 8-core system. Heterogarnet produce a much shorter average and tail latency than DICE. Moreover, even if we adjust the mean latency for heterogarnet to approach DICE, as in HG+, we still cannot match the long tail behavior. HG+ moves the average, but it does not reproduce when and how delay variation occurs in phi links because Hitcher-Garnet Plus still uses a fixed latency model without modeling all the detailed phi link behaviors. Further, we observe that the same phenomenon happens in other graph benchmarks too, where the gap between HG and dice cannot be just closed by adjusting the average latency alone. Similar problems happens to synchronization-heavy multi-threaded applications. The key result on this slide is the multi-threaded application slowdown. Here, we show the difference of running the same program using single-threaded and multi-threaded mode. Each mode involves 3 cases, running with monolithic cores, which is the implicit baseline here, with chiplet systems using Hitcher-Garnet, and using dice. We can observe that for a workload like XS bench, which is memory intensive and synchronization sensitive, dice predicts much larger slowdowns than fixed latency models. In the most extreme case, multi-threaded dice reaches about 10 times the monolithic runtime. By looking at these examples, the takeaway is phi link overhead is not just an additive fixed latency. It is shaped by packet delay distributions, contentions, synchronizations, which are all affected by the detailed phi level behavior such as errors, packet resending, error code encoding and decoding. Thus, we need simulation tools that model not only the logical network, but also the physical behavior of phi links. This motivates DICE, which models detailed phi behaviors. DICE is a detailed inter-chiplet end-to-end phi model integrated into Gen5. It models high-bandwidth phi link data transmissions in detail, including SerDes behavior, encoding and decoding, modulation, channel noise, and retransmission effects. It is configurable through Gen5 Python configuration, works in both full system and system emulation modes, and the default parameters are based on industry practice and open datasheets, and we validate DICE against real processors. Our goal here is not to replace architectural simulation with a circuit simulator. Our goal is to capture the essential phi effects that are architecturally visible while keeping the simulation overhead low enough for architectural studies. Now let us examine how DICE works. At a chiplet boundary, packets moves from one router on one die to another router on another die. In a fixed latency model, this is done with counting a predefined latency, and then move the packet to the next router. DICE adds all the missing physical communication steps. A data fleet is encoded with forward error correction. The encoding get buffered, and then get modulated, and then the packet is translated into a signal waveform, which will be transmitted to the next router. So this means the router model and the phi model must interact. If decoding succeeds due to smaller channel noise that we have seen here, the receiver sends an ACK acknowledgement, and upstream resources such as buffers can be released. If decoding fails, probably due to larger noise channels, then the receiver send instead a NAC, and the transmitter must resend the packet. Here we have two important resources of delay variations that cannot captured by fixed latency. First, The decoding process is iteration-based. The number of decoding iterations depend on the received signal quality, so the latency is not always the same. Second, if the receiver cannot correct the data, the message must be recent. Retransmissions are rare under good channel conditions, but becomes often in bad channel conditions. When channel quality decreases and retransmission happen, they create long tail delays. And all of these cannot exactly be modeled with fixed latency models. Next, I will break down the main 5 components model in DICE. The first component is called forward error correction. DICE use FEC rather than only CRC. CRC detects error, but if an error is detected, the message must be retransmitted. FEC tries to correct likely bit errors at the receiver, which reduces transmissions. So how this works, in DICE, a fleet is the data payload, for example, 128 bits. The encoder adds parity bits to form a code word. The parity is generated using a base matrix, and the implementation follows a low-density parity check style structure. I will not go into the details here. The important architectural point is not the exact matrix operation. The important point is that the outgoing fleet becomes a protected code word, and this extra protection affects the reliability and packet resending process. After encoding, the digital bits must be sent as physical signals. DICE supports several modulation schemes, including NRZ, PM4, QPSK, and 16 QAM. The example here focuses on PM4, which is widely used in high-speed links. PM4 sends 2 bits per symbol by using 4 voltage levels. With gray mapping, the 2-bit patterns 00, 01, 11, and 10 are mapped to 4 amplitudes, plus minus 150 milliwatts and plus minus 50 milliwatts. So here we can see, depending on the bit pattern appear in the input, the corresponding voltage is produced, and ultimately the input bit stream will be translated into a signal waveform. Why DICE models this? DICE models this because once bits becomes voltage levels, channel noise can move a received symbol closer to the wrong decision boundary. In this way, DICE has a way to model physical signal quality instead of just flipping a bit. This affects directly decoding iterations, retransmissions, and eventually architectural timing. The next component is the channel noise model. DICE model noise as additive white Gaussian noise, or AWGN. The effective signal-to-noise ratio, or SNR, depends on several factors, including the base channel SNR, jitter, and crosstalk. I will once again not go into details. The important idea here is that DICE does not simply assign a fixed probability of a delay. It models how the transmitted signal is distorted by channel conditions, and then let the receiver logic determine whether the data can be recovered or a resend is needed. For example, when the channel quality is high, let's say 35 on decibel, the received PM4 symbol are well separated and the decoding is easier, and we may not have any resending. All the errors are shown here in this red box. However, when the base SNR drops, for example, to 15 decibels, which means the channel becomes now noisier, the symbol clusters overlap more. This increases uncertainty, increase decoding efforts, and may increase the chance of a retransmission. And the modeling channel noise is how dice connects physical channel quality to packet timing. At the receiver, dice performs demodulations and FEC decoding. The receiver computes log likelihood ratios, or LLRs. An LLR is a soft confidence. It does not just say whether a bit is 0 or 1, it predicts how confident the receiver is that a bit is 0 or 1. These soft values are passed to the FEC decoder. The decoder uses parity constraints to correct likely bit errors and reconstruct the input data stream. If the code word is corrected, the receiver sends an ACK and upstream buffers can be released. If the code word cannot be corrected, the receiver sends a NAC and the sender must resend the data again. This is the key end-to-end connection. Analog channel distortions affects demodulation confidence. Demodulation confidence affects FEC decoding, and FEC decoding affects the sending of X or acknowledgement. And all these affect packet delay and architectural performance. We're not going to review much details about how this works. More details are in the paper. Next, I will show the main results. I will focus on runtime overhead of dice and validation of dice against the real processors. So first, what does dice cost? Detailed modeling is useful only if the overhead is practical for architectural simulations. We measure dice overhead using a recently proposed Gen5 crosstalk profiling methodology and tool. The tool is available here and published in ISPAS 2026. This breakdown shows that the iteration-based decoding is the largest additional cost in dice. This is expected because the decoder may perform multiple times of decoding. From the figure, we can also see that memory-bound applications such as graph applications, BC, BFS, CC, and synchronization-heavy applications such as Axis Bench also create more overhead. This is because they generate more cross-chiplet traffic and therefore exercise the PHY model more often. Over all 14 programs, the average runtime overhead is about 10%. From the accuracy we gained, this is a moderate overhead and keeps dice useful for architectural studies. Next, we would like to show the validation results of dice against real hardware. The main validation shown here compares tail core-to-core latency against an AMD EPYC 9454P system. This processor has multiple CCDs, so core-to-core latency reflects both intra and inter-CCD core-to-core latencies. In the figure, we showed core-to-core latency from every core of one CCD to every other core in the system. And this is heterogeneity. Heterogeneity produces a smoother latency curve. This is consistent with its fixed latency Inter-Chiplet model. It captures the broader structure of how a chiplet system works, but it misses much of the delay variations because it uses an oversimplified inter-chiplet communication model. DICE closes the gap to real EPYC 9454P measurements. More importantly, it captures the variation pattern better, because packet timing is influenced by the detailed PHY behavior rather than by a constant delay. Actually, this gap could be closed further by fine-tuning dice parameters for the exact processor and the exact packaging technology. But even with default parameters based on industry practice and public information, dice already gives a much closer match than a fixed latency model. And here we show a visualization of the previous results. So we first look at the critical latency of the real epic system. And this is how it looks like in heterogenet. We can see that all the critical latencies are consistently underestimated. The middle one is the critical latency under dice, which closes the gap to the actual platform much closer. We also have more validation results in the paper, including Threadripper and another version of Epic. So, to conclude, detailed file behavior matters now for chiplet simulations. Current architectural simulators often model inter-chiplet links as fixed latency connections. DICE aids all the missing details. For example, DICE models end-to-end file modeling. It models encoding, modulation, channel noise, demodulation, FEC decoding and encoding, etc. The broader message is actually, as processors move further towards chiplet-based integration, architects now need simulation tools that model not only the logical network, but also the physical behavior of inter-chiplet communications to study its effects on architectural performance. If you are interested in our work, we will see you in session 7A on July 1st. Thank you.